Okay, guys, for today's our topic discussion will be influence lines, and particularly we will be discussing how to draw the influence line for determinate structures, for the finding reactions, the shear force, and the bending moments. So, starting with the bending moment and shear force diagrams, bending moment and shear force diagrams show the variation of bending moment and shear force along the structural element. For example, beam. When a load is applied to the structural element, points of action of these loads are fixed. Okay, so till now you have discussed that either a point load at a fixed point or a UDL at some given distance or a UVL is applied to the beam, and you have to determine the reactions, and you have to determine the shear force and the bending moments along the length of the member. These diagrams are useful to determine the maximum bending moment and shear force developed in the member and the locations of the maximum values due to the application of the loads. Okay, so in order to design, you need to find out the maximum values of shear force and bending moment so that you can design the members. Similarly, you have to distinguish between the points. For example, in structure 2, you will be moving to the indeterminate structures, and in that section or area, you have to find the support bending moments, which is most of the time negative bending moment. So you have to differentiate between positive moment and negative moment and all this. Okay, so this is the main purpose of bending moment and shear force diagrams. And you already know the sign convention for negative and positive values. For example, if you are taking the section from the left, like this one, you have taken the section and the member is on the left, so downward shear will be positive. This anti-clockwise, which is pushing or causing the member to bend in the upward direction, is positive, and this force in tension is positive. Okay, similarly, if you are taking a section at a right, sorry, at a left, and the section or the member is on the right, so everything will be opposite. The downward shear is now negative. Here upward shear will be positive. The tension is in the opposite direction, and the clockwise movement is now causing the section or the element to move upward. So I have explained these terminologies. This is the positive normal force. Okay, since this force, axial force, is causing uh, tension in the member, so it is called positive. This is positive shear. Okay, and as I told you before that at the right edge, or if the element or member is on the left, then downward is positive, and upward on the other side will be positive. Similar to the bending moment, this bending moment is causing the uh, uh, member to bend in a way that the top fibers are in compression and the bottom fibers are in tension. So this moment is taken as positive. Now for a beam, a given load P is presented here at a fixed point. Okay, this is a fixed point. The load is not moving. The load is constant. It is at the middle of the beam. So the procedure is simple. The reactions, since the load is applied at the middle of the beam, so half of the P will be reaction at both the supports P by 2 and P by 2. Okay, so the shear force diagram will be, it will go upward up to P by 2. Then since there is no load up to the middle of the beam, so there will be a 0 degree diagram. Okay, and at this point, the P, since the value is P by 2, so this P will make it 0 and then negative P by 2. Okay, and it will go with a 0 degree curve till this point, and this reaction of P by 2 will make it 0. So your shear forcing diagram is closing, and the bending moment diagram, the supports are hinge and roller respectively, so there will be 0 bending moments. Now the area of this diagram will be P by 2 into L by 2. So it is coming into up to this point. The magnitude is P by 2 into L by 2 is PL by 4. Okay, and then this area, it will make it 0. So this is your positive bending moment diagram. Okay, so in the difference is that in previous example the load was applied at the middle, at the center. However, in this example the same axial load is applied at a different distance. For example, if the length of the beam was 10, then this load is applied at a 5 feet. Okay, however, in this case, if the length of the beam is 10, then let's suppose this load is applied at 7 feet from this support and 3 feet from this support. So accordingly, you have to find the reactions, and you have to draw the shear force diagram and the bending moment diagram accordingly. The point where there is a shear force is 0, then there will be maximum bending moment at that point. This is our old concept and we already know this. Okay. Now coming to the UDL, this is our uniformly distributed load. The load is constant, the load is not moving, and it is applied throughout the length of the member. So our reactions will be W into L divided by 2. So WL by 2 and WL by 2. So what will be the shear force diagram? It will go up to WL by 2. Since the load diagram is 0 degree, so the shear force diagram will be 1 degree and it will become 0 at this point. So this is our shear force diagram, and since the shear force diagram is 1 degree, so the bending moment diagram will be 2 degree. Okay. And the magnitude of the bending moment diagram, you can find it by the formula, or you can find it by the area of this triangle. Now this is the case what I discussed at the beginning of the lecture, that in structural analysis too you will be analyzing some indeterminate structures with different methods. Okay, we are not going into that detail, but consider this indeterminate structure with this fixed support and these three roller supports. Okay, so there will be a negative bending moment at the fixed support, positive bending moment at the center, then negative bending moment at the support, then positive bending moment at the center of the span, then negative moment, positive, negative. Okay, this is your bending moment diagram. See, you can see from here M, and this is your Q, which is shear force diagram. These are your shear forces, right? And these are your reactions. So these reactions, draw shear force diagram and draw bending moment diagram. Please keep in mind that what we were discussing in the class, we considered negative to be on the downward side. However, here they are considering negative bending moment at the top, okay, and positive at in the bottom of 0 0. So there is no difference, just opposite sides. And there are two way of representations, and one of them is this one, which is we are noticing here, so don't get confused. Now coming to the influence lines, that after understanding what is shear force and bending moment diagrams, what is influence line? When the applied load is not fixed. Okay, so, till now we were discussing about fixed loads, right? We have seen 4 or 5 examples, and in all of them the load were fixed. But what if a load is moving? For example, you have seen bridges, right? And on bridges the loads are moving. For example, huge trucks or trains or even pedestrian, the small bridges are made for the pedestrian loading, right? So what if the load is moving? In that case, we use influence lines to determine the impact of live moving loads. See, at a single point as the load moves across the beam. So it says that if the maximum load, for example, you have designed a pedestrian bridge for the people to pass upon it. So we consider that, okay, if what if a 100 kilogram man passes through it, and what will be the maximum effect, that at what point the man will be on the bridge or the beam, so that it is having the maximum effect or the maximum shear force or bending moment producing in that member. So influence lines are important in the design of structures that resist live moving loads. So in case of bridges, particularly, the influence line diagram is very important. Now this is an example that this is a simply supported beam AB, right? And there is a point C. Point C is at a distance A from support, at a distance small a from support capital A. Okay, we have a unit load which is at distance x from A. So what is the influence line diagram for reaction at B? See, this is for reaction at B. Please keep in mind, this is very important terminology. Okay, so we are talking about reaction at B. So there will be a unit reaction, one. See, one unit. We have applied one unit and we are joining it at this point. So what is this? You will know this, that how this diagram is obtained. But at this point, just consider this as a triangle. So what is the height of this triangle? The height of triangle is 1. And what is the base of this triangle? The base is L. Okay, so this is another triangle at distance x. So we know the base x. What will be the height at this point? So it is, from similarity of triangles, it will be x by L. Okay, similarly, if you have to produce reaction at A, see this influence line diagram for reaction at A. So the triangle will be other way around, right? It is opposite to that triangle. So at this point, if you have to find the equation or the height of this triangle, right? So it will be 1 minus x by L. Okay, it is simple. It is from similarity of triangles. Similarly, if you have to find force or react or shear force at point FC C, so influence line diagram for FC. Okay, it is shear force diagram at point C. So this will be your influence line diagram. I'm again telling you that don't get confused that how we obtained this diagram. This lecture is about drawing these influence line diagrams. So right now it is just showing you that at a specific point, for example at a distance x, what will be the values. So the here you can find it from similarity of triangle, that it's x by L, and this is bending moment diagram, and you can find this perpendicular by x into L minus A whole divided by L. Now, definition of an influence line. An influence line represents the variation of the reaction, shear, moment, or deflection at a specific point in a member as a concentrated load moves over the member. Okay, so you can draw the influence line diagram for reaction, for shear force, for bending moment, or for the deflection, right? As the concentrated load or a point load is moving across the length of the member. They provide a systematic procedure for determining how the reaction, shear, moment, or deflection in a given part of a structure varies as the applied load moves about on the structure, right? So as the live load is moving along the structure, it provides you the systematic procedure, okay, for determining these reactions, shear, movements, and or deflections. Now, what is the difference between influence line diagram and bending moment diagram? The difference between constructing an influence line and constructing a shear or moment diagram is that influence lines represent the effect of a moving load only at a specified point on a member. Okay, so if you remember the previous example, see, here we had a point C. So I want to see the effect of this unit load when it moves from A to B. What will be its effect at point C? Therefore, we are saying that it is to represent the effect of a moving load only at a specified point on a member. Okay, so you have fixed a point and you want to determine the effect at that fixed point. Similarly, bending moment diagrams represent the effect of fixed load at all points along the axis of the member, right? So it is opposite. Here in influence line diagram, the load is moving and the point is fixed, where you have to determine the effect. However, in bending moment diagram, the load is fixed and you have to determine the effect at all the points along the axis or along the length of the member. Understand it? Now, what are the different methods of producing influence lines? Take a moving load of 1 unit weight. 1 unit weight can be 1 kip, 1 pound, 1 kilogram force, It can be 1 Newton, 1 kilonewton, whatever units you are working with, it doesn't matter. But take a moving load of 1 unit weight, right? Select the point of interest. You have to determine a specific point where you have to determine reactions, shears, movements, and or deflections. Okay. Place the moving load at various points. You have to place the moving load. For example, if the length of the member is 20 feet, you just say that, okay, I want to place it at 1 feet. So you have to find 20 different points. 1 feet, you have to put the load on 1 feet and determine the reaction at the specified point. Then 2 feet, 3 feet, 4 feet, 5 feet, up to 20 feet. Okay. Similarly, you can make the interval as 2 feet. That I want to put the load at 2 feet distance, 2 feet, 4 feet, 6 feet, 8 feet. You can put at 4 feet, at 5 feet. It's up to you. Plot the values of the reaction, shear, movement, or deflection over the length of the beam, computed for the point under consideration. Okay. So place the moving load at various points and plot the values of reaction for that point. Okay. Now, methods of producing influence lines continue to make life easier. For statically determinate structures, you get straight lines, although the line slope may change as the load passes over key points. Okay, so in statically determinate structures, what we are dealing with in the structural analysis one, you get the straight lines, so it makes your life easier. Okay, it's not of that much, it's not that difficult, so don't get worried. This is again the same thing which I told you previously, the influence line diagram for a beam with the unit load applied at a distance x, and the point of interest is at a distance is the point C, which is at a distance a. Both the distances are from the left support, which is a. So I already explained these things to you, but we will discuss that how to draw these diagrams. Okay. Why use a unit load for an influence line? So an important question, that why you are using a unit load. Number one is easy to multiply by the weight of anything or any number of things I want. Okay, so one is a unit. If you want to do for a 25, you can just multiply 1 by 25. If you want to do it with the 35.35, so you can just multiply it. If you want to do it for 53.75, you can do it. Okay, so it doesn't matter what value you are using, but you are using one here, so you can just simply multiply anything and you will get your results. Second, influence lines are popular for studying the impact of moving variable loads on bridges and other structures. To obtain the reaction, shear, movement, or deflection due to any applied load, multiply the ordinate of influence line diagram by the value of the load. Okay, so it is very simple that you got the values, for example, PL by 4. You know the L, you just multiply the value of P and you will get the results. So it's simple. Okay, so if you are using 1, just multiply the influence line with your load and you will get the desired results. Influence line represents the effect of a moving load at a specified point on the member. Shear and movement diagrams represent the effect of fixed load at all points along the member. We already discussed this thing. Now, the important thing is procedures to determine influence lines. Okay, so there is a tabular procedure and there is a influence line equations procedure. Okay, so there are two procedures. The first procedure, which is tabular procedure to determine the influence line. In both the procedures, the step number one is same: place a unit load. Okay, and this is the pace of this method, that place a unit load uh, at a point, and you don't know the exact location of the load, so it is the point at distance x. Okay, and you can vary the value of x. Then use the equations of equilibrium, summation of f of x, y, and moment, to find the value of the function. See, the important thing in this method is you determine the value of a function. You are using equilibrium equations to determine the value of function in terms of this x. Okay, and then you have to put the value of x. Okay, and you have find the values of these shear, moment, and reactions. Repeat step 1 and 2 for various values of x over the whole beam. For example, x is equal to 2, 4, 6, 8, and 10. and you are repeating the step number 1 and 2, and then plot the values of reaction, shear or moment for the member. So this is the tabular procedure in which you are using equilibrium equation to find the function, and the second one is a direct method in which uh, you are using influence line equations procedure. The step number 1 is again same. What is step number 2? Use the equilibrium equations to find the value of reaction, shear or moment. See, now here you don't need to find the value of the function. So you are directly determining the values of shear, moment and reaction with equilibrium equations, and then plot those values. Okay. So these are the two methods we are using, and first we will be making equilibrium equation in method number 1 for the analysis of determinate structures. So what does it says? Structures such as bridges and overhead cranes must be designed to resist moving loads as well as their own weight, right? Since structures are designed for the critical loads that may occur in them, so influence lines are used to obtain the position on a structure where a moving load will cause the largest stress. Got it? Influence lines can be defined as a graph whose ordinates show the variation of the magnitude of certain response function of a structure as a unit load transverses across the structure. And response functions of a structure may include axial forces in members, support reactions, bending moments, shear forces, and deflection at specific points in the structure. So you can draw influence lines for all these response functions or any of them which is required. Now, a shearing force or bending moment diagram shows the magnitude of the shearing force. Okay, we have discussed this thing in detail. Okay, that what does a shear force or bending moment diagram shows, in where the load is fixed and you have to determine the values all along the length or the longitudinal axis. Okay, and in the influence line diagram, the load is moving and you have to determine the uh, function at a specific point. Now, to grasp the basic concept of influence lines, consider the example beam shown in figure below. Statics help to determine the magnitude of the reaction at supports A and B, and the shearing force and bending moment at a section N. Now, where is section N? See, the load P is this, which is at a distance X. However, the section N is at a distance B from support on right and distance A from support on left. Okay. So as a unit load of arbitrary unit, for example, its unit can be 1 kip, 1 pound, 1 kilogram, 1 newton, whatever. It moves from right to left. So this load is moving from right to left. Okay. And while it is moving from right to left, you have to determine the uh, effect of shear force and bending moment at section N, right? Now, the first step is the beam reactions, taking the moment about B as the unit load moves a distance x. For example, in this case, see, so take the moment about B, summation of all the moments about B are 0, and it is taking counterclockwise as positive. So RA is producing a clockwise, so it is negative, right? And P is making a counterclockwise, so it is positive. So minus RA into total length plus P into distance x is equal to 0. To determine the RA, it will be P into X divided by L. Since P is equal to 1, so put 1 in this equation. So RA is equal to X by L. Now you remember the previous slides where RA was X by L. You remember? Okay, don't worry. You will understand it much clear in the coming slides. So this is the expression for the computation of the influence line for the left and reaction of a simply supported beam. Okay, so you want to determine the reaction at A, so you have to know where the load is applied. For example, if X is equal to 2 and L is equal to 10, so what will be RA? 2 divided by 10, 0.2. Okay, and what will be RB? 0.8. Got it? Now, the influence line for RA can be represented graphically by putting some values of X into the equation. Since the equation is linear, 2 points should be enough. So it says that, as you can see, that the equation is linear, a 1-degree curve. Okay, so it says that two values are enough. Now, for example, what if X is equal to 0, and what if X is equal to maximum? So putting X is equal to 0 will make it 0, and putting L is equal to maximum, x is equal to maximum, which is L, Ra is equal to 1. So when x is equal to 0, Ra is 0. When x is L, Ra is 1. So it means that when x, as you know that if we are moving from right to left, okay, please keep in mind. For example, here it says that you are moving from right to left, okay. So the load is moving from here. Here it is 0 and here it is L. So when the load was here, Ra was, this is Ra. Ra was 0, and when the load is moving towards the support A, when it is at L here, Ra is maximum. So all the load is resisting here by Ra. So this is a 1 degree curve, a linear equation. The graphical representation of the influence line for Ra is shown in figure below, and the ordinate of the diagram corresponding to any value of x gives the magnitude of Ra at that point. Now you have this diagram. If you have the magnitude of P, for example, P is 52 kips. So just multiply this diagram with 52. You have get 52 kips here maximum when the load is at support A. Okay. Similarly, the expression for the influence line for reaction at B is found by taking the moment about A. So take moment about A is equal to 0, for example here, right? And my RB into L is counterclockwise, so it is positive, and P is making clockwise, so it is negative. See, if this is X, so this distance will be L minus X, right? So P into L minus X. So from here RB will be P into L minus X divided by L. Now use two values of X. For example, number one is 0 and number two is L. So setting P is equal to 1, you will get L minus X divided by L, and putting two values of X will give you, when X is equal to 0, RB is maximum because P is at this point, and when X is equal to L, so load is here and reaction will be 0 at RB. Okay, so as the load is moving away from support, the reaction at support B is reducing linearly, and it is opposite to RA. See. Okay, now coming for the shearing force at section N, because in this statement, if you remember, it says that statics help to determine the magnitude of the reactions at supports A and B. So we have determined the reactions at A and B. Now the shearing force and bending moment at section N. Okay, now shearing force at section N. When the unit load is on the right side of the section, the shearing force at the section can be computed considering the transfer forces on the left side of the section as follows. For example, for example, when the load is on the right of this section, so for example in this case, okay, this is the case when this load is on the right side of this section, and the second case will be when it is on the left side of the section. Okay, so when it is on the right side of the section, the shear force at this section NN can be computed considering the transverse forces on the left side of the section as follows. Shearing force V is equal to RA. Since at this section, if you are taking this section, okay, only consider this section, there is only RA. When you are taking force from the left side, so the shear force at this section will be equal to RA, right? And what is the magnitude of RA? That is X by L. See here. So Ra is equal to X by L, putting both the two conditions when X is equal to 0. So put it here is X is equal to 0. So V is equal to 0, right? And put X is equal to B. Why we are not putting X is equal to L here? See, the answer is here because we have to determine at section N, right? So when X was 0, the load was here, and when it will be maximum, when it will be at section N, because at section when we take X is equal to L, it will be at support A, it will not give you the maximum magnitude. So first boundary condition was X is equal to 0, and then X is equal to this B, right? So putting X is equal to B, So your shear force will be equal to B by L. When the unit load is on the left side, first we consider it on the right side, right? If the unit load is on the left side, for example, if this P is here and it is exceeding this limit B, because first we considered that the unit load is on the right side, so we took from 0 to B. Now it is exceeding B. Okay, so what will happen? It is easier to compute the shear force in the section by considering the forces on the right side of the section as follows. So now we are considering, here we consider the forces on the left side, here we are considering the forces on the right side because the load is on the left side. So simple, V is equal to minus RB, right? And which is equal to RB is equal to L minus X divided by L, right? So now please keep in mind that here we took V is equal to RA because RA was in upward direction and V is in downward direction, and we saw the sign conventions in the initial slides. Okay, so please go to that slide and check why we are taking it here, because we are taking right side, so it should be upward but it is not upward, so we're taking it as a minus. When x is equal to b, see, here we took x is equal to 0 to x is equal to b. Now we are moving forward further from b to L, so here we are taking x is equal to b and then x is equal to L. Okay, so here when we are putting b here, so you are getting minus a by L, b by L, and suddenly minus a by L. So the section N is the point where your shear force is changing from positive to negative. Okay, and when your x is equal to L, your will be equal to 0. So at support B, your forces will be 0. At support A, your forces will be 0. And the maximum force will be at section N. I'm talking about shear force at N. Okay, here you can see the graphical representation. So you started from here, so it was increasing till your section N, and it reached its maximum value of B by L, and at the same section N it drops down to the negative value when you took the other side, or the other half of the section. Okay, so it comes down and then it again reaches to the 0 value, right? Then considering the bending moment in the same way, just multiply the load with the distance. So if you are clear with the shearing force, for example these equations, then you will be much clear with the bending moment. Okay, so here in M, you just multiply this RA with the distance L minus X. Why L minus X? Let me take you to the initial condition. See, this is your L and this is your X. So L minus X gives you this distance, right? So the bending moment that is caused by this load will be equal to this load and the distance. Okay, all right. So RA into L minus X, put the value of RA, which is X by L, and put two values again. It is like a shear force that the limit is from 0 to B. Okay, so one you put 0, other you put B, so you will get these two equations. Then the secondly, if you are taking the other side of the section, so RB into X, and it will be equal to L minus X divided by L into X, and put the two values of X is equal to 0 and X is equal to B. Okay, so it will give you the value of uh, moment is equal to 0 and moment is equal to AB by L. Now the question here is that why we have used the same limit of 0 to B, right? So the answer is that if you clearly see both the equations for the bending moment, for example, this bending moment when you are taking RA is X by L into L minus X, and when you are taking bending moment with RB, it is against the same L minus X into X by L. So if you are putting B here, so L minus B is A, right? So this gives you A, and this is X is equal to B, so AB by L, right? Similarly, if you are putting A here, So L minus A is B and this is A. So AB divided by L. It doesn't make any difference in the bending moment if you are using x is equal to B, the boundary condition, or x is equal to A, the boundary condition. So here you can use very clearly x is equal to A or x is equal to B, whatever suits you. Okay. This is the influence line diagram for the bending moment at section N. 0 0 when the load is at support, and the maximum bending moment when the load is at the section, and the value of the bending moment is A into B divided by L. Now you will know the value of A. For example, A is 4, B is 6. So 4 into 6, 24 divided by 10, so 2.4. And if you know the value of the load, the magnitude of the load, then just multiply the magnitude, for example 25 into 2.4, and you will get the value of your influence line diagram. Okay. So this is about the drawing the influence line diagram for some given value with the equations to determine the function. And in the next video we will continue with some more examples, for example from here, that how to find vertical reactions, shears and bending moments, and we will also discuss the other method as well. Okay, so we will be continuing in the second video. Thank you.